Spoilers.
Dude, yeah, it's just like, it's like random people. Yeah, I just have to, I have 2 tickets for my mom and dad, and then Vicky and Amelia wanted to go, and we both gonna be there. Yeah, I don't know, he might go next year. He also has like some family stuff going on. He's leaving on like the 16th, so, yeah, so he's not coming back. Yeah, he technically doesn't finish till next fall, and he's thinking about taking the fall off, and then just doing the spring, and like finishing on time in the spring. I think he's got like a pretty good internship this summer, so he's kind of can like gear up for grad school apps.
No, I heard, yeah, I think maybe your 2 extra were already put up into the extra one, and maybe like that's what, I don't know. I know a lot of people were like selling theirs and like, I thought about it, but I just didn't know how much.
I noticed too that it's definitely clear that you have to register
这个 S 就是说，这个 S 其实你的意思是说，你必须要对任何一个 S 都能解一个方程，你必须要对任何一个 S 都解一个方程，最后才能够把它恢复回来。如果说你对于有些 S 你解不了的话，所有可能不会碰到这个，对，所有的 S 都必须要能够解。是的。
所以说这是，就比如说，如果要取这个细节的话，就直接任意一个特权嘛，这种随机取一个 S，
是的，
就能给出一个。
那就是说什么？就是不是随机取一个，而是所有的，只不过所有的它们共享能够被同样的一个式子写出来的，它们可以被同样的归结于这样的一个，因为这里我们很巧的是这里的 A 跟 B 它跟 T 没有关系。因为它没有关系，所以说它所有东西都是只是在实际上进行平替而已，是无所谓。但如果说这里呢，小齐最要讲的是，如果说这里 A 跟 B 它跟 T 有关系，其实还没那么简单。那这样的话 ，GST 它就未必是一个方式在实际上的完全平替法，那就不一定。Okay, let's resume. So, I hope those are ready to be back in a couple of minutes. So, you see, the biggest idea of the Green's function so far is that, let me try to write it down, okay? So let's say I'm having a LF, okay? F is a function, Lx, which is a function, that equals to my f. F is also a function. Again, that was in the context of ODE. L has to be L is a linear operator. Okay, L is a linear operator. X is a function. F is also a function. So, so the problem that we're facing is that the linear operator is sending a function to a function. Okay, and we would like to solve the inverse problem. How do we go back from f to x? How do we go back from f to x? But the problem is that this differentiable operator, as we said in the first class, is usually non-invertible. That is usually non-invertible. Actually, most of the time, I cannot obtain such a thing, which is called L inverse, simply because the differentiation, the step of differentiation is actually non-invertible, right? And in order to do that, the idea behind it is that if I could tear my f apart, if the f could be teared apart, okay, into many pieces, in our scenario that was something like ft equals to the integration from infinity to infinity fs, okay, delta t minus s ds. Okay, if my ft could be teared apart into a linear combination of many small pieces, each of the small piece is the delta function, a delta function spatially translated at some point, okay, and equipped with a weight, okay, related to f. If my f could be teared apart into many small pieces, then we could first solve the equation, okay, for every piece, or more specifically, we obtain something like LGS, okay, which equals to delta t minus s. Then do linear combination back. Okay, then do the linear combination back. But you see, so before we see, this is everything. This is already everything that we have just talked about in this in the first half of this lecture. But you see, the problem is that actually over here, I have never said the f has to be what? X and f, they have to be single dimensional function. I have never said this, right? My x and f, they can be arbitrary dimensional functions, as long as they are defined on the same space, defined for the same independent variables. Right? So when my x and f becomes higher dimension, and when my L is no more a ordinary differential operator, but becomes a partial differential operator, this becomes what? This equation becomes what? This equation now becomes a partial differential equation. Okay. So when L is a partial derivative, my LU, okay, I'm not using x anymore. I'm coming back with the notation in partial differential equations that we are familiar with. My LU equals to f. Okay, now this becomes a partial differential equation. Is a partial differential equation. Is a my LU is there. Now it becomes a partial differential equation. N can be tackled. Okay, N can be tackled exactly with the same idea. And this is something that we're not going to do today, but we will be postponing to our last class. Okay, which actually belongs to chapter 12.2. Okay, which is how do we utilize? So what we have just done, what we have just illustrated. For the Green's function, that's like a warm-up. For ODE, that's like a warm-up. Okay? And in the next class, we'll be more specifically talking about, okay, how do we reapply this idea of the Green's function to every single type of linear partial differential equations that we have already encountered. Okay, including wave equation, diffusion equation. These two equations on the whole space, these two equations on the within a small interval, equipped with different boundary conditions, and of course that also include Laplace equations and Poisson's equations. Okay, but before we come back, okay, to the context of partial differential equations, we first need to get into 12.1 distributions. We first need to have a very rigorous Okay, at least more rigorous than before. We need to have a rigorous definition and understanding about what is the delta function. What is delta function? You see, we have already talked about so many properties. See, we have already talked about so many properties about delta functions. Delta function, the value of delta function is what? The integration of delta function is what? Delta function can be regarded as a derivative of what? Okay, and delta function convoluted with other functions are of what? But you see, all these things are treating the delta function like a piece of machinery, like a tool, like a handful tool, without looking into what exactly this tool. See, so before we come back to the context of partial differential equation and apply the delta function very extensively, okay, into our discussion, we will be first cover using the section 12.1, okay, to cover a mathematically rigorous discussion about what is delta function. Okay, what is delta function? So the delta function, so before we get into the detail, let's first give the specific definition. Okay, definition. The delta function, or instead of talking about delta t, let's still use delta x. This is something that we are more familiar with in this class. Okay, the delta function is a rule. Okay, is a rule or a operation such that okay, it always assign phi 0 to function phi x. Okay? It usually assign the value phi 0 to function phi x. So what does that mean? That means that delta function, let's say, if I'm seeing my delta function x, okay, again, let me call it as an operator. Let me call it as an operator. Let's say we have been using. What is a good way to say this? I have already used L. I have used D. Okay. Let's say delta function is an operator D, and D is a mapping. D is a mapping. The mapping D, okay, is always sending a L1 function. Is always sending a L1 function defined, let's say defined on the whole real line. We already know what is meant by an L1 function, right? The delta function is always sending a L1 function, okay, to a real number. It's always sending a function. So you see, function is doing what? Function is always sending a number to a number. Operator is always doing what? It's always sending a function to a function, right? And here the delta function is something in between. It's not a function. It's nor it is an operator. It's a mapping always sending a function to a real number. It's a mapping that's always sending a function to a real number. Or more specifically, D is always sending phi x. Okay, phi x is a function, right? Or let me use the square bracket. Phi x to phi 0. D is always sending phi x to phi 0. How is that achieved? How is that achieved? Well, this is achieved by taking the linear product. This is achieved by taking the linear product. So, more specifically, D phi x, D phi x. This is exactly the linear product between delta function and phi, which, okay, this is the definition. This is the definition that I choose. Okay, this is the definition that I choose. And equals to, therefore, equals to phi x multiply, so delta x multiplied by phi x, and then integrated from infinity, positive infinity to positive infinity, and finally I obtain phi 0. Is that right? But is there anyone having any trouble seeing the last step? Is there any trouble seeing the last step? No, right? This is because of what? This is because, first of all, phi x, you see, in most of the places, in almost all the places, my delta x is 0, right? Therefore, the phi x is only relevant, the value of the phi x is only relevant when x is 0. As long as I choose my phi 0, other things are completely arbitrary. They are out of the equation. Okay, they are not considered by us for now. Okay, and the other thing is that after I substitute the phi x to phi 0, then this becomes the integration from negative infinity to positive infinity about phi x. Oh, sorry, about delta x. Okay, and then with a constant phi 0, of course. Finally, I obtain phi 0. Okay, I hope there's no questions for this step. Okay, this is the idea. Okay, this is the idea. And also, it actually has a name. It actually has a name as distribution. Okay. It also has a name as a distribution or function. Or functional. So this is the definition number 1. Now the definition number 2. Definition number 2. A distribution F wait a minute, so let me, sorry about that, let me put it this way. Okay. So let me first define what does it mean by a functional. A functional, okay, a functional, this is not a function, it's something being applied on the function, okay? A functional is a mapping, sending a function to a number. Okay, a functional is a mapping. Is always a mapping, sending a functional to a number. And therefore, delta function is a functional. Okay, delta function is a functional. Since delta function by using the linear product, the delta function is always sending a function to its value at 0. So it's always sending a function to a number. Okay, my delta function is a functional. And definition number 3. Definition number 3. A distribution is a functional that is both linear and continuous. Okay. a distribution is a functional that is both linear and continuous. Okay, so there are two different types of property. Well, actually, the linear part is actually somehow easy to understand, right? The linear part is somehow easy to understand. So, by linearity, okay, by linearity, we actually mean that, okay, so let's say that a distribution f, is a functional, okay, that is both linear and continuous. By linearity, we are saying that, okay, for arbitrary functions, for arbitrary phi and psi as two functions, we're having that f is sending a phi plus b psi to a f phi and plus b f psi. So you see, first of all, f is a functional. F is a functional, right? And f is a functional, so f is always sending a so that means that for an arbitrary function, f is going to send this function to a number. So f is sending phi to a number. This is a number. Okay, this is a number. F is also sending psi to a number. This is again a number. And linearity means that for any linear combination of phi and psi, f is always sending this linear combination to the exactly the same linear combination of these two destinations, of these two numbers. So far so good? So far so good? Okay. And this is what is meant by linearity. And another thing is by continuity. What does it mean by continuity? You see, I was saying that a distribution f is a functional that is both linear and continuous. What does it mean for a linear functional? We already know what does it mean by a linear function, right? What does it mean by linear? Oh, sorry. What does it mean by a continuous function? What does it mean by a continuous function? A continuous function means that if I'm moving, if on the x-axis I'm moving a little bit, but then on the y-axis I'm also moving a little bit, right? Okay. If I'm approaching someplace, if I'm approaching x, then the function value will absolutely approaching fx. This is the definition for continuity. But what does it mean by continuity of a function norm? How do you imagine a definition for a function norm using the idea of the continuity of a function? Function, again, continuity of a function is that when I'm approaching x, the value fx is approaching. Let me rephrase this. I'm on the x-axis. When I'm approaching a certain point x0, the function value is approaching fx0. Okay. Can you use the similar idea to come up with the continuity of a function norm? That means that now I'm not moving on the x-axis because now the independent variable is no more x anymore. I'm now moving in what space? A function space. When I am moving myself in the function space, when I am approaching certain function phi x, then the output of the functional is going to approach f phi x. Sounds good? Okay. So now by continuity, when in a sequence of functions phi n, okay, satisfy that phi n is approaching phi. Okay, phi n x is phi n x is approaching phi x. Okay, when n goes to infinity, then f phi n, okay, the output of f phi n is approaching f phi. The output of f, oh, sorry, not equal, really, but actually should be approaching f phi. Okay, so that's it. This is a, and again, what does it mean by the approaching, right? At least we have already learned at least one thing, one way of approaching, the L2 approaching, right? The L2 metric. Okay, that's what in one sense of approaching. And of course, there's another way of approaching, which is the uniform convergence, right? Again, what was the common for the uniform convergence? That was the L infinity approaching, right? That was the L infinity approaching. So we are having different ways to approach a function, but as long as we are using certain ways of approaching, then my f phi n should approach f phi. Okay? So, okay. Well, that means that, okay, that means, okay, that means, that means that my delta x, okay, my delta x is a distribution. Okay, my delta x is a distribution. My delta x is both linear and continuous. Okay, my delta x is both linear and continuous. Well, so this is actually our example number 1. Okay, example 1. And again, this is about the discussion. It's about the discussion of delta x. Okay, it's a discussion of delta x. Okay, example number 2. Example number 2. Can you please tell me what distribution is always sending, okay, what distribution is always sending phi x to phi x to, let's say, not to phi 0 anymore, but to phi 5. What distribution is always sending phi x to phi 5? Delta x minus 1. Again, this is a distribution. It's linear and it's continuous. Okay, so that's good. And, well, example 2.1. Example 2.1. Assuming that we are talking about functions whose second order derivatives exist and are always always finite. Okay? Can we say that is functional sending phi to phi prime phi a distribution? Is this guy a distribution? Which means that, first of all, is that linear? Is this a linear functional? Is this a linear functional? If we are having, let's say this functional is something like, let me call this functional to be something like g, okay? So which means that g phi always gives me something like phi prime phi. This g, first of all, is g linear? Okay. This is because of what? This is because A phi plus B psi actually equals to, A phi plus B psi prime evaluated at 5, right? And this is exactly a phi prime I valued at phi plus b psi prime I valued at phi. So in D. Okay, it's linear. Is that continuous? Okay, it's well actually the continuity of this should actually require some more delicate requires some more delicate validation. This is because we were only saying, you see, we were only saying that, okay, when, what does it mean by phi n approach phi? When phi n approach phi, there is no actually guarantee that their derivatives always also approach, right? No guarantee, there's no guarantee. Because the function actually can approach 0, but maintain that it's indifferentiable everywhere. It's indifferentiable almost everywhere. Okay, there can be such a function. There can be such a function. So if you want to verify the continuity of such a functional, actually we need to define, the function space, this function space probably in another fashion. But here let's not mingle too much, with the definition over here. Let's just say that this function g is also a distribution. Okay, it's both linear and continuous. Okay. Example number 3. Example number 3. Let's say I'm having another functional. Okay, a functional h. Okay, h is always sending phi to something like the integration from negative infinity to positive infinity, fx phi x dx. Oh, you know what? I don't quite like this. What about I just simply do something like? Okay, the integration from negative phi to phi, okay, and 3 multiplied by phi x dx. Question. H, of course, is a functional because it is sending a function phi to a number. Okay, this number is again an integration. Integration of 3 multiplied by phi x and integrating from negative phi to phi. Okay. Question. Again, is that a distribution? Is that linear? Is that continuous? Is that linear? Is that continuous? It is linear. Right. It's actually very easy to verify that. This functional is linear. Is that continuous? Well, you see, in both in the L2 sense or in the uniform sense, we can have that. If one function is approaching, if a sequence of functions is approaching phi, then of course this integration will also approach. Right? Okay. So this is also a functional. Oh, sorry, this is also not only a functional, but a distribution. Okay? Here's a distribution. It's a distribution. And example 3.1. Example 3.1. And now my H star is mapping phi from infinity, negative infinity to positive infinity, fx multiplied by phi x dx. The question is that if this H star, is that a distribution? Is that necessarily a distribution if I pose no requirement at all on f? Is that definitely a distribution? Is that definitely a distribution? Is it definitely a distribution? Doesn't have to be, right? It doesn't have to be a distribution at all. If my f is not integrable, right? If my f is not integrable, then I can easily design a phi x, okay, that is sending this integration to infinity. Okay, that is sending this integration to infinity. Then there's nothing that's called continuity. Then there's nothing called continuity. So usually here, if I want my H star to be a distribution, then actually we always require, okay, to to make H star a distribution, okay, to make H star a distribution, we need fx, okay, to be integrable. Okay, we need fx to be integrable. Okay. And one specific case is that 3.2. One specific case that now H star is something like 5, or okay, actually not 5, but D is sending, okay, from infinity to point infinity, is sending, always sending, sorry. H star is always sending phi x, okay, to the integration between the product of delta x and phi x dx. Okay, and of course, this is always going to give you phi 0. This is always going to give you phi 0. But again, this is completely for notation. Okay, this is completely for notation because this is not really an integration. This is not really an integration, and my delta x is not really a function. Okay, not to say an integrable function. Okay, so this is completely notation-wise. Okay, and you see, we have been talking about so many things, so many setup, okay, about the distribution. So we can finally talk about a theorem, or we can finally talk about a convergence, the definition of convergence of distribution. Convergence of distribution. What does mean the convergence of distribution mean? That means that for all function, let's say test function, I'm going to explain what does it mean by test function very briefly, okay? For all test function phi, you can regard the test function as something that's called regular function, okay? Because in many cases you can always design a bizarre function to make everything fail. So for any test function, so that's okay. Let me put it this way. A sequence of distributions. Fn is converging weakly. Okay, actually I should stress this. Converging weakly, okay, to another distribution F, if and only if for any test function phi we have, when n goes to infinity, Fn, okay, the target Fn sending phi 2 is exactly the target of F sending phi. So that's good. Because of what? Because you see, again, function is what? Because distribution is what? Distribution is a functional. Functional is doing what? Functional is such a thing we define upon function, right? Functional can never really exist individually. Okay, the existence, the legitimacy of functional depends solely on the function. Okay, therefore, any properties of the functionals, okay, are always tightly bounded, okay, with the function. Therefore, when we are talking about convergence of a sequence of functional, we're actually talking about, okay, the convergence of a sequence of number. It's just that these numbers are exactly the targets of functions sending the function to. So is that good? So is it good? Is there anything unclear about this part? Is there anything unclear about this part? Okay. So let me quickly give you an example. Okay. Now again, before we proceed to the example. Now the test function, okay, the test function means a carefully designed space of functions such that okay, the operations are equal. Again, you don't have to worry too much. You don't have to worry too much about if about the specific meaning of this, because we are not, again, we have no intention to proceed to functional analysis. Okay. Okay. So let me give you an example. Let's say my fn, okay, again it's a functional, okay. My fn exactly equals to delta x minus 1 over n. The question is, does my fn converge weakly to f such, okay, does my fn converge weakly to the delta function? Does it converge weakly to the delta function? Yes or no? Or the thing is, or the question, to answer this question, you ask yourself, is that true that when I'm pulling, or when I'm pulling any function phi into this, this sequence of delta function is always sending this function to something that's close to the value of its origin? Exactly. So now you have found a trick, right? Actually, here we need to pose a request on the test function phi, which is what this function has to be continuous. If this function is continuous, okay. So let's see the arguments. Okay. So argument. There are two parts of the argument. The first part is that if phi x is always continuous, okay? If phi x is a continuous function, then what can we say? Then my fn is sending phi x to what? Then my fn phi is always what? My fn is always sending the phi to what? Phi 1 over n. Right? Phi 1 over n. Since my phi is indeed a continuous function, so when n goes to infinity, my phi 1 over n is that indeed converge to phi 0. So is it good? But if phi x is discontinuous, well, then there's nothing can be said. Right? There's nothing can be argued anymore. Okay? There's nothing can be argued anymore. This is because if phi x is discontinuous, then, well, when x approaches 0, there's nothing to be guaranteed. It can be anything. It can be anything. Okay. Well, let's come up with one more example to finish this class. Okay. Let's come up with one more example to finish this class. So, Actually, two examples. So example 4 and example 5. The source function. Okay, the source function. Is there anyone remembering what does it mean by a source function for the diffusion equation? Sxt equals to what? Sxt equals to what? 1 over square root of 4 pi k t, and then e the negative x squared over 4 kt. This is the source function. Okay. Okay. The argument is that the source function, okay, sxt, the source function, it does converge weakly. Okay. Sorry, let me put it this way. Yeah, okay. It does converge weakly to delta function. To delta function. Okay. When t approaches 0. When t approaches 0. Why is that? Why is that? Because we have proved what? We have proved that. We have really proved that when the integration from negative infinity to positive infinity, sxt, okay, and then phi x dx, okay, when t goes to 0, we have proved that this actually converges to phi 0. Right. This is something that we are proving in chapter 3. So the source function indeed, it approaches to the delta function, okay, weakly when t goes to 0. This is an example, and don't forget, what is the shape? What is the shape? What is the shape of the source function? It's always like a Gaussian, right? It's always like a Gaussian. It's just that when time evolves, the Gaussian is becoming flatter and flatter and flatter and flatter. But if we evolve back in time, then this Gaussian is actually becoming thinner and thinner and thinner and thinner and thinner. Right. So that's, again, let me try to say this again. If I am not talking in the sense of distribution, not talking in the sense of converging weakly, then this is nonsense. Okay, this convergence is nonsense. Because of what? Because first of all, the delta function is not a function at all. I can't say any function is converging to this function. Again, because it is not a function at all. Second thing, sxt, when t goes to 0, sxt is not approaching anything at all. Because of what? Because at 0 it's approaching infinity. It's not converging, it's diverging. We can only talking about the convergence of the source function to the delta function when t goes to 0, only in the sense of distribution, only in the sense of converging weakly. Okay? If we're not talking in the context, okay, of distribution, then there's no convergence. It's going to be illegal to say that, okay, sxt converging to something. It's not converging to anything. But again, in the sense of distribution, well, we are treating sxt not as a function, but as a function norm. It's converging. Okay, it's indeed converging to a function. Okay, this is the example number 4. And a very tightly related example number 5 is the Dirichlet kernel. I bet some of you have already forgotten what does it mean by a Dirichlet kernel, right? It's the kernel that we used to prove, okay, the pointwise convergence of Fourier series, or more specifically speaking, knx, okay, knx is exactly 1 plus 2, the sum from n from 1 to big N cosine nx, okay, which this guy actually equals to sine n plus 1/2 x over sine x over t. Okay, this is the Dirichlet kernel. This Dirichlet kernel, okay, this Dirichlet kernel is converging weakly to 2 pi, okay, to 2 pi. Yes, to 2 pi delta x, okay, but this delta function is not defined on the whole real line. Okay, this delta function is defined on a periodic space, okay, from negative pi to pi. Or if you want to extend it, okay, if you want to extend it to the whole real line, this knx, okay, this knx is actually approaching something like this. It's actually approaching something like this. Okay, 0, this, 2 pi, this, 4 pi. Like a periodic delta function, negative 2 pi. Okay? This again is because of what? This again is because that, okay, this is because, okay, this is because we have already proved, that from the integration from negative pi to pi, knx, okay, phi x dx is actually approaching 2 pi phi 0. Okay. When n goes to infinity. Or probably let me write everything in the sense of limit. When n goes to infinity. Okay. This is what we have proved. In order to prove the pointwise convergence, right? In order to prove the pointwise convergence for the Fourier series. Okay, so I guess this is a very good timing for us to conclude the lecture today. I'm going to upload the homework. Okay, and you can start to do it right now. It's going to only be covering sections 12.1 and section 12.2 for everyone to have a very basic understanding of the distribution. And I strongly encourage you to finish the homework as much as you can, because the relevant questions are, well, there will be I would say one question. Okay, there will be at least one question that is about distribution and functional. Okay, in our final exam. Okay, so probably it's a good idea to still look into that. So thank you everyone for coming. I look forward to seeing you in our last lecture on Wednesday. Oh, by the way, the teaching evaluation. I think you have already received the email for teaching evaluation. Actually, probably it's a good time. If you have some time right now, okay, can you please try to put it out and then log into your account and then do the teaching evaluation right now. Yeah. Because that, I mean, our response in the class usually can help us to increase the response rate. And your opinion will be very important for us.
Will we have a chance to review it on Wednesday?
Sorry?
Will we have a chance to review on Wednesday a little bit?
You mean review everything on Wednesday?
Yeah.
I suppose so. I'm only designing the materials for like 70 minutes, 80 minutes, and the rest of it is going to be.
There's no class Monday or Wednesday. No class Monday.
Because it's going to be the final.
Yeah, Wednesday is okay.
It's going to be, because our final is next Wednesday.
Was the exam the whole semester, or is it just some?
It's mostly the second half, but when anything is referred to in the same in the first semester, it's going to be referred to naturally. Yeah. It would be very nice if you could finish the teaching evaluation before you leave the classroom. Thank you very much.
朋友来你们学校来听课。
可能应该是累赘的，应该是累赘的，或者说是根本的 class space。
我说吧，我已经把那2封邮件都删了，我以为是没有用的。就是我找不到邮件，叫啥名字来着？就是应该，多久发的？我老娘啊！就是主要是这么多未读邮件，基本上是很明显的垃圾邮件。垃圾邮件你删掉吧，你不用管它。我的2封邮件，他给我发2封，但是我全都删光了。偷你的气，就是他应该不在 birthday 上，你在 over 上面真的 over 上没有。你不，等，你点这里看看。不是你点一下看看。
啊，
我他只能点一下上去，直接点看看。那还有就是点他比较清楚。
我想去，但是我没有。
我也没有客气，有一个点。而且估计今天有个估计他会有下就是OBE 我就这一下。让我看了呀。哦 ，first speaker 是吧？
可以啊。
啊，你是写这个写的。
哦，没有，我看一下。但是我应该没有。
没有。不可能作业，我觉得做上的，他会上去。
我还没学到作业。
我作业里面有一个这个很小的，哎，问一下其他同学有没有收到那个feedback？哦，对，点他们，然后你递上去。哦，有点像，是过去来了。哦，来了。啊。
Actually，因为我还没学。我马上要去学。
3题我才参去。哦。就是这个。我也好困难，这个教室感觉有点缺氧。我们学校这还算离阳台近的，可以随时开个空气。太有强度。我去，我忘了停，我还在录课。